I mean, he's my collaborator, and he have given a lot of helps to me. He will speak about products of three primes in large arithmetic progressions. So, sir, please start.
Okay, thank you for this invitation, and I'm happy to speak in this beautiful conference. I'm very unhappy not to be there. It's like I was saying, it's the first time I had a 1-year visa to come to India, and this 1-year visa will expire in 2 months because in February last year I was in KSOM. Anyway, let's talk about primes and happy things. So product of primes in arithmetic progressions. Since the audience is very varied, I'll go slowly and I'll try to repeat things. Okay, at the beginning, you have Dirichlet, who proves that if you give yourself a modulus Q and a residue class A, which is prime to Q, then you can find infinitely many primes that are congruent to A mod Q. Of course, you have to assume that A is prime to Q, otherwise you won't find so many. And it was an old question started by some work of Euler. Many people gave wrong proof. Yes, Legendre gave a wrong proof and so on. So this paper was really a fundatory paper. I just mentioned that Dirichlet is a tenfold forefather of mine. You can have fun with math genealogy and find your forefather, but through Desouillet, Halberstam, Rademacher, blah, blah, I go back to Dirichlet. Okay, okay, I'll say a bit more about this theorem later. But of course, once you know that you can find a prime and infinitely many of them, the next question is to know how small can you find them. There are two questions: how regular is the distribution, and how small can you find one of them? I mean, what is the first one? That's what I call the Linux problem, and many people call it the Linux problem. So find B of Q, so that for any residue class A prime to Q, there exists a prime less than B of Q, so that P is congruent to A modulo Q. So if you look at all the primes from 1 to Q, you have only Q open log Q of them. And most probably they are not going to be enough to cover all the residue class because you have some gaps between them. That has been proved long ago. So B of Q by Q tends to infinity. That has been refined by Pomerantz in the 80s and recently by Lee and Shakan. So it's something like Q times log Q times log log Q times log 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 Q, and it's very small. Okay, so what can we tell about B of Q and GRH? So the generalized Riemann hypothesis. We can show that B of Q is less than Q to the 2 plus epsilon. It can even be made rather explicit, and there's some work of Barr and Sorensen in 96. Some recent work of Lamzouri and Lee, another Lee, and Soundararayan that qualifies this Q to the epsilon. You want to get something even better, closer, and so we know that B of Q is between Q plus or minus epsilon, plus epsilon, and Q square plus epsilon. But in fact, the true maximal order of B of Q is not known. I mean, the poor man's argument is to say that B of Q should be Q1 plus epsilon, and that's what I believe, and many people believe that. But it's really because we don't see why we should argue in another way. But there's no real argument that says, okay, look at, I don't have any argument that says, look at this sum, and there's some cancellation here, so the true order is Q. The Linux in 44, 45 proved a wonderful theorem that this B of Q is less than Q to the L. So for every Q, I mean, there is an L which is uniform. At the beginning, it was 10,000. So this L is uniform for all Q. So that there is a prime less than Q to the L. And you can choose this prime congruent to A mod Q once you choose A. There's been some fight after that to get the value of L given by this proof. So it started by 10,000 in 56 and it got down till Chen and Liu in 89 to 13.5, I think. And then there's a fundamental paper by Hisbrown in 92, really an excellent work where he gets the value L equal 5.5. In this paper, he presents some, he says, okay, I didn't do all the improvement possible. And this was done by Xiluris in his PhD in 2011. So the published paper has L equal 5.18. But in fact, in his PhD, you can find 5. It has not been published. I don't know why. I've not been able to get hold of Xiluris. So I don't know whether there's a mistake somewhere or whether it was too complicated, too long to publish it, and no journal accepted it. Anyway, let's say that for the time being, L is about 5, and it's valid only for Q large enough. And we have absolutely no idea how large this large enough can be, because the proof is complicated. Okay, so let me tell you a bit about the nature of this problem, especially for people from outside our world. It's a typical additive multiplicative structure problem. I mean, we mix those two structures. The first multiplicative structure you can see, it's you ask someone to be a prime. That's easy. The additive structure is more difficult to see here. It's in the size condition. When you ask that the prime be less than x, you're looking at the order for the addition. So that's where the additive structure enters in this problem. It's very important to note that. Then you may wonder about the condition congruent to A modulo Q. Is it a multiplicative? Is it an additive condition? You'll see the way it is treated. Sometimes it is treated as an additive condition, and sometimes it is treated as a multiplicative condition. Yeah, it depends. Something else about this result that is important, and I'll tell you more about that later, is that it's breaking parity, in the sense that we ask for a prime to be congruent to A modulo Q. We are not asking for an integer having at most 2 prime factors. So we control the parity of the number of prime factors. That's something that's important because of some difficulty later. And yeah, so this breaking parity is something that you should really have a look at. So there's a specific mystery in this problem, which is a multiplicative group Z by QZ. I don't know whether you can see the star here. This very simple object, which is a finite abelian group, is extremely mysterious. You can see it because you have difficulty handling character sums, short character sums. It's a very elementary object and very difficult one to grasp. So sometimes I will add also a fully explicit angle to what I'm saying. Explicit, you may say, when I say L equal 5 or 5.18, it's explicit, but it's not fully explicit because it's Q large enough. When I say fully explicit, I want Q larger than 10 to the 10, L equal 5.5. Yes. Okay, so I don't know what is next. Oh, yes. So if we skip a prime, there's nothing much I can do. I mean, I told you what we know how to do. So I'm going to relax the condition of being prime, but I want to keep the nature of the problem. So relaxing the condition is going to be, I'm going to ask for a product of 3 primes instead of a prime. but I keep the parity. We are asking for product of 3 primes, not for product of 2 or 3 primes. There's some, yes, okay. And we want all of these primes to be small. So we're still in the same kind of problem. Some people like Sparlinski and Walker, they relaxed the parity condition. They look at the product of at most that many primes in congruence condition. It's a different stream of research. There's a funny conjecture by Erdős. I don't know exactly when Erdős stated that, because Erdős stated so many conjectures. At least you can find it in a paper by Erdős, Odlyzko, and Sarkozy in 87. And this conjecture says that products of exactly 2 primes less than q cover z by qz star. And if you do some computation, you discover that it's not exactly correct, provided q is larger than 7. But once it's larger than 7, it should cover z by q star. I didn't have the opportunity of talking with Erdős about this conjecture because I discovered it only recently. Okay, but in the method, you should see that the case p less than q and p less than q to some eta with eta strictly larger than 1 are completely different. They're completely different because if you ask that p is less than q and p is congruent to a, you have at most one of them that is possible. So these 2 cases are completely different, and I'm looking only at p larger than q to some eta with eta strictly larger than 1. Well, it can be 1 plus epsilon, but really, it's this kind of problem that we're looking at. Okay, in case some people forgot, the number of primes less than x is pi of x. It's about x upon log x. Yes. I'm also telling that because you know, there's Riemann's memoir in which you find the Riemann hypothesis. It dates from 1859. Dirichlet's theorem that I stated is 1839, 20 years before. And many people say that the prime number theorem for arithmetic progression has been proved by Dirichlet. That's false. Dirichlet proved that the primes were well distributed in arithmetic progression, but he didn't know how many of them there were. Yes. Chebyshev's memoir is in 52 only. It's only in 96, so 60 years after Dirichlet, that we proved the prime number theorem. And then the equivalent for arithmetic progression was proved by de la Vallée-Poussin some years later, essentially in the same year. De la Vallée-Poussin had not finished his PhD when he proved the one for arithmetic progression. So that I'm using Wikipedia a lot, and I'm trying to correct Wikipedia when I can, but just be a bit careful about what Wikipedia says. Okay, so primes in arithmetic progression number 2, the theorem of de la Vallée-Poussin is the one which is in the middle. You want to know the number of primes less than x that are congruent to A modulo Q. That's easy to guess. In Z by Q, Z star, you have only phi of Q congruent classes that are prime to Q. And so you say that the primes are well distributed among this residue class. So you should have x upon log x divided by the number of classes. So x upon phi of Q upon log x. That's what de la Vallée-Poussin showed. In fact, building on the work of Dirichlet. And then now, of course, we ask the uniformity in Q, which means how large x is with respect to Q. I'm going to state some work of previous student of mine, so that you can have an idea of what we are able to do. Explicitly and theoretically, it's also good. When Q is larger than 10 to the 30, not so small, and non-exceptional, forget about this condition. It's really to simplify things. And x is larger than Q to the log Q. right, to the 5 log q. So it's not q to some power. It's q to something that goes to infinity. And that goes to infinity like log q. Well, you can find a prime in an arithmetic progression and properly localized. So that's what we're able to do from an explicit viewpoint, and when you want only one prime. Okay, now I'm going to make a detour. And since I was not able to be in Kerala, I decided to give you some pictures. This one is a picture from Kerala. It's a lake. It's a picture by Dimitri Koukoulopoulos. I stole it from him when we were in KSOM 2 years ago or 3 years ago. Okay, this detour is towards some work of Ramachandra and Balasubramanian. Sorry, Balasubramanian and Ramachandra. And I have to tell you about the Bronte-Schwarz theorem. This is a theorem that I've stated in the middle. So you look at the primes that are in an interval of length x, primes between y and y plus x, okay? So an interval of length x, and you want them to be conjoined to A modulo q, okay? It turns out that the sieve gives you an upper bound for this number. So this upper bound is about, assume that x is much larger than q. So log x by q is log x. So it's twice x upon log x, which is the number of primes between 1 and x, divided by phi of q. So essentially, this upper bound is twice too big. You lose this factor 2. Now let me tell you some things around this theorem. The name Bronte-Schwarz is due to Linig in 61. In fact, Titchmarsh proved the theorem of the similar flavor, and he was using a method of Brun. So Linig decided to call it the Bronte-Titchmarsh theorem. And now we have Brun-Titchmarsh theorems, different variants of it. This one is a variant due to Montgomery and Vaughan. There's no error term. It's 2, not 2 plus little of 1. It's 2, exactly 2. In fact, Brun didn't prove it with 2. He proved it with a constant, and we're very happy with that. And Selberg in 46, I think 47, obtained the factor 2. He didn't notice this factor 2 either. He said, okay, I have a constant, it's 2. It's more explicit than with Brun, and I'm very happy with that. And then we discovered that this factor 2 was fundamental. I'll tell you more about it later, but we really cannot break this factor 2. If you break this factor 2, you'll be immediately famous. That's what I said, better than 2, oops. Okay, now let's see what we can do with that. And I want to show you that this one is an extremely powerful tool. And to do that, I'm going to use some work of Balasubramanian and Ramachandra's. They published some papers in 76. Balu must have been very, very young at that time. Okay, look at this sum. 1 plus cosine y to the small power times log p. So it's a non-negative thing that you're summing, 1 plus something, okay? And you sum around primes between y and 2y. And since if you don't know anything about the primes, you know the primes, you have only y upon log y. It's very thin set. Maybe 1 plus this cosine could be 0. If you don't know anything about the primes, this cosine could always be equal to -1, and that may happen. So how to prove that it's not equal to -1? Well, if you use analytical means, the derivative of this one is y to the 20, I mean, the derivative of log p is 1 upon p. So essentially, it varies in interval of length y to the power 1 upon 20. And analytical means cannot localize the primes in intervals smaller than square root y. That's what you get in the Riemann hypothesis. Riemann hypothesis tell you that you can go till square root y. Usually you go till y. So y upon to the power 1 by 20 is really out of reach. So analytical means you cannot do it. If you use Vinogradov, I mean, you use bilinear forms. Maybe you don't know what it is, but it's the second big manner of getting handling this kind of sum. It's not going to work in this case because you have some multiplicative sum. You know, it's the cosine is exponential something. So because of multiplicativity, this sum is not going to be cannot be treated by linear sum techniques. And still, Ramachandra and Balasubramanian are able to prove that it is larger than y upon log y. How you do that? Well, you use the Bronte-Schwarz theorem. You see, this function repeats itself in interval of length about y to this small power. And what the Bronte-Schwarz tells you, forget about the phi of q and the q part, just take q equal to 1. What the Bronte-Schwarz tells you is that the primes cannot accumulate at the very bottom here. I don't know whether you see this up here, maybe better. It cannot accumulate at the very bottom here. I mean, it will have, better, okay. It will have to spread a bit on the side because here it's going to be little of y upon log y if it stays here. That you can do with the Bronte-Schwarz, and you cannot do with the two main methods for handling primes. Okay, now that I've told you that, I've cheated a bit because you may want to be clever. You may tell me, oh, what is happening? Okay. You may tell me, well, you don't need to know the way primes are distributed in every interval of length y upon 1 upon 20, but in most of them, almost all of them. So you can try and use that. And okay. And what we know how to do, we know how to handle interval of length y upon 1 upon 10 by Harman, essentially. Maybe it has been improved in between. I'm not so sure. That's why I put y upon 1 upon 20. So I'm sure that this one we're not able to handle it now. But on Riemann hypothesis, we can handle it. So what I want you to understand is that the Bronte-Schwarz theorem tells you that the primes cannot accumulate. I mean, they are spread in some manner. So you see the Bronte-Schwarz theorem, you have two parameters. You have the length, x, and you have the q, which is the progression. I showed you how things work in the x aspect, and then you may ask the question, what about the q aspect? And in fact, that's what I was doing in. I mean, I was giving a talk in Bordeaux about this method and how you do it in q aspect, because I was using the same method in q aspect for handling sums of 7 primes. You know, there was a beautiful work of Linick also in the 40s saying that every large enough positive integer is a sum of 7 cubes, 7 positive cubes. I mean, non-negative cubes. And of course, the question was to know what was the largest of the ones that was not sum of 7 cubes. And it was believed that it was 454, and I was working on that. This has been finally solved brilliantly by Samir Siksek in 2016. He shows that really the largest integer that is not sum of 7 cubes, 7 positive cubes, it's 454. And he uses, one of the ingredients is this method. So when I was giving this talk, Aled Walker was in the audience. I was saying, okay, I'm blocked here. There's something that you cannot, there's a hurdle that you cannot overcome. And he said, well, you know, I think I know how to overcome this hurdle. So that's another picture. Because since I cannot be here, I can at least be in some funny places. This one is a picture from Mukoti Peak on top of Uti. And you may wonder where is Kerala. Well, we are looking west, and Kerala is at the bottom of the mountain that you see over there. Okay, so we started talking with Aled, and here's a result that we finally obtained. if you select a prime congruence class A modulo Q, well, you can find 3 primes, so exactly 3 primes that are rather small, so that P1, P2, P3 is congruent to A modulo Q. So why was it exciting? Well, first, this result is completely explicit. It's Q larger than 1. But the exponent is not so great. 16 by 3, well, 16 by 3, it's 5.3. So it's not even as good as Xiluris 5.18. But it is explicit. That's the very good part is that the proof is done in 4 or 5 pages. That's why we're excited about it. The other part is the ingredient it uses. Because we are going to use sieve, we are going to use some additive combinatorics, and we are using some weak information on primes in quadratic subgroup. And essentially, we believe that none of this ingredient was able to break the parity principle. It turns out that we have very simple proof of that, and I'm going to show you this proof. So the first one is to tell you that there's enough primes between 1 and x. You have to add the condition p prime to q, okay? But you know the number of primes less than x is about x upon log x minus 1. The minus 1 is at the denominator, which means that's x upon log x plus infinitely many of them, and that's enough to do that. So that's an explicit version due to Pierre Dussart, and it's easy. The second version that I've recalled is Bronte-Schwarz theorem only in Q aspect. So I've removed the interval. It's a simpler version. Okay. Still with this factor 2, with this log x by Q. And with that, what can you do? Okay. So look at the primes between 1 and x that fall into classes in Z by QZ. Okay. All these primes are prime to Q because you've removed the other ones. You have x upon log x of them. And you know that in each of these bin, in each of this class, you can have twice too many that on average. The conclusion is that at least half of these bins are full. Okay. Because it's not, you don't lose the factor 2, but you lose a bit more. It's not that half of the classes, but half minus something. In fact, if you take the parameter and you have the log x by q, where you lose a bit more even, finally you get 1/3 to some delta. So what the Bronte-Schwarz theorem tells you, just like before, is it tells you that the primes cannot accumulate in a single class. They spread. And they spread in a positive, in a set that has a positive density with respect to the full density. Okay, the third ingredient is very simple. I'm going to state it when Q is a prime. If Q is a prime and you look at the squares, the residue classes modulo Q are split into squares and non-squares, 1/2 on one side, 1/2 on the other side. Of course, all the primes less than Q, say, cannot be squares, because otherwise all the integers up to Q would be squares. They are product of these primes. So one of these prime is a non-square, and you want to know whether there's a prime that is also a square. And that you can do. You can find a prime less than even P, even less than P. Explicitly, that's what we've proved with Aled, because we wanted very, very simplistic method. So you can find a prime less than 25Q square. That's easy. Okay. And the final ingredient is additive combinatoric. So additive combinatoric, that's a theorem, most probably it has been proved in the 50s. How things are, you have a set A, and you are in G by QZ star, which is a multiplicative group. It's a finite abelian group. You have a set, you want to look at the product of this set. I mean, the elements that are product of two elements of this set. And you believe that the product set is going to be bigger than the initial set. And if you look at the integers between 1 and n, and take capital A of them, well, you believe that A1 plus A2 are not going to accumulate in a single, it's not going to repeat themselves. They are going to be very different usually. And that's usually what happens. The worst case is when you have your set is between 1, 2, 3 till A. And then when you see A plus A, you get 2, 3, 4 till 2A. So you get 2A minus 2, which in terms of cardinality, it's 2A minus 1. So that's what we believe is that when you start from a set and you look at this double set, okay, multiplicatively speaking, it's A times A, you get 2A minus 1 in cardinality at least. But in finite abelian group, we have an additional problem. A could be a subgroup. If A is a subgroup, A times A is A. So you haven't saved anything. So you have these two extremal cases. Either you have a subgroup, either you have you're like in Z. Okay. And Kneser's theorems tell you how to go from one case to another, because you see, A could be also a coset of a subgroup, a single coset. Then A times A is going to be a single coset also. But A times A could be two coset modulo a subgroup of small order. So you have lots of things to understand, and that's being given by Kneser's theorem. Essentially, Kneser's theorem tells you that look at the number of subgroup that A times A crosses. I mean, look at the stabilizer of A times A, sorry, and look at addition in G by H. That gives you the answer. Okay, in our case, we have our set A, which is the number of primes. I mean, the class is rich by the primes. G is the multiplicative subgroup. And you know that the set A has at least phi of q by 3 elements, even more. So what can be the stabilizer of A times A? If the stabilizer is G, the full group, it means that A times A is the full group. So you're happy. You have everyone already. If the stabilizer is a subgroup of order 2, well, it's not possible, because I know that in A times A, you have a quadratic residue and a non-quadratic residue. That's a small lemma I showed you about quadratic subgroup. Then you deduce that A, the index of A is at least 3. And once you know that the index of A is at least 3, and you know that the cardinality of A is larger than G by 3, you're home, and you can prove easily that A times A times A is a full group. Why 3 times? Because A times A gets double, it gets 2/3 of phi of q, times 3, it gets 3/3, which is a full group. Okay, some comment, and then first comments and then second comment. First comment is that, so the parity principle, I told you about that a bit. It's something due to Selberg when he was trying to understand what sieve were doing. And essentially, it's something that says that sieve cannot distinguish between the parity of the number of prime factors. It's a bit vague. It means that when you count primes, usually you count product of 2 primes. You cannot get only primes by only sieve. Then you have the factor 2 in the Bronte march. That comes naturally. And that we know that it is equivalent to the parity principle, essentially because the factor 2 comes from the fact that you're not counting primes, but also product of 2 primes. So one for the primes and another one for the product of 2 primes, with no small prime factor in. And the third problem, which is linked with that, we know that the factor 2 in the Bronte march is linked with the class number 1 problem. When you want to know that, if you remember the talk of Kumamoto, I guess. If you want to show that the class number of q of square root of minus q goes to infinity, for instance, it's the same as showing that L1 chi is infinitely larger than 1 upon square root q. And we know that this one is equivalent to the breaking the factor 2 in the Bronte-Schwarz theorem. It's very easy proof. Ramachandra has a proof in half a page of this fact. If you see in the proof we have, we use only the factor 2 in Bronte-Schwarz, so we don't break parity. We use a lower bound for L1 chi, but the lower bound for L1 chi we use is 1 upon q. So it's not enough to break parity. But still, at the end, we have exactly 3 primes. We don't have 2 or 3 primes, or 1, 2, or 3 primes. So what happens is that we don't produce the good number of primes. The parity principle has to do with counting. It has to do with counting exactly the same number on one side. And since we're plugging some combinatoric in between, we don't get the good number of primes. We get maybe, yeah, we don't get x upon log x upon phi of q. We get much less than that. So that's the good point is that we managed to avoid this obstruction. The second remark is that when you have the class number problem, if you remember previous talk and Bhargava's cube and so on, you have an algebraic structure. But if you look at the factor 2 in Bronte-Schwarz, you've lost the algebraic structure. In this proof, thanks to Knesser's theorem, you see an algebraic structure that appears again, which means that you're able to feed in your problem some more information. Okay. I'm going to continue. This one is also India, of course. It's from Mahendra Giri in Orissa. And we are looking, I don't know, maybe southeast. I didn't take this picture. It's beautiful. Okay. So once we have a method that we believe is good, we started investigating it with Oriol Serra and Priyamvad Srivastava, and then with Balu and Priyamvad. And this work is in progress. It's essentially completed, but we have to, I mean, the paper is written, but now it's too big and it has to be split in parts. Anyway, so here is what we obtained just now. If you take Q a bit large, but not too large, you can find primes P1, P2, P3, so that the product is congruent to A modulo Q. And this time these primes are less than Q to the 5/2. So the 5/2 is much better than the 16/3. It's 2.5, so it's much less than the exponent we have for Linux constant. Even if you take the product of 3 of them, no, the product of 3 of them is too large. Okay, but at least each one is small. What is published is a work with Oriol and Priyamvad, where we had Q to the cube. But the method we had with Oriol and Priyamvad was blocked at 3. We are already happy to have managed to go below 4, but we were stuck at 3, and now we have 5/2. But of course, I told you that Linux constant, we guess under GRH that it's between 1 and 2, and 5/2 is still larger than 2. So can we go below 2? And well, if we omit the explicit aspect and we take the same method, except that it's much simpler, we can go till 3/2. And 3/2, that's really between 1 and 2. And even if you take the product of 3 of them, you get 9/2, which is less than 5. So that gives a much, much better exponent. And the method is still the same. I'll tell you more about it. I have to go a bit faster. If you take the recent work of Petrov and Young, assume that Q is cube free, you can reduce this 3/2 to a 4/3, and you can do some other things. Okay. So what are the questions, the issues that we have to cover? If you remember the proof I've given, you first have to get a good density, a large enough density for your set, and that's done by a Bronte-March inequality, or a modified form of the Bronte-March inequality, but the sieve has to enter the game to get a large density. That's the beginning of your work. Then you have to go from densities, knowing that a set is big, to individual representation. And that's what Knesset's theorem does for you. We'll add another theorem from additive combinatoric by using P2 numbers. It's an addition, but so additive combinatoric is going to take care of that part. And then you have to take care of, we have the problem with coset in quadratic subgroup. In fact, if you want to go to a smaller exponent, you'll see subgroup of index 5 appearing and subgroup of index 8. And to handle them, well, just now we use any trick. I told you at the beginning, to prove that there is a prime which is a non-quadratic residue, you use the fact that all the integers are the product of all the primes. It's a combinatorial trick. To prove that there's a prime which is a quadratic residue, you use L1 chi. We'll use some result on L functions. Aled used some averages of multiplicative function to prove a partial result. And there's some result from algebraic number theory. You'll see that this part is essentially wide open. Okay, so let me present some more. Bronte-March inequalities first. Beautiful IE by Priemvad. If you look at Bronte-March inequality, but you don't count the primes in one class, but in a full coset, U times H is a full coset, and H is a large subgroup. I mean, it's a subgroup of index Y, and assume that Y is small. Y is 5. What we can get is that you can get the Bronte-March bound 2x upon y, which is what you have. But instead of x upon q, which we had before, we have x upon square root q. That's where we save in the density, because x is some power of q, and it's allowed to be lower because of this square root q at the denominator. What is rather amazing about this result, it's that it's even valid when q is less than x. The Bronte-March inequality, x has to be larger than q. Here, x can be up to square root of q. I mean, a bit larger. Let me see. Okay, some notes on the proof. Yes. First, okay, let's see here. So the Bronte-March inequality you recover when y is a subgroup of index phi of q. Y is 1. And of course, you get x upon y times square root of q, log q. So it's essentially y upon q to the 3/2. And in Bronte-March, you have x over q. So when y is very small, we have better results than the usual Bronte-March. And when y is large, Bronte-March is better. It would be better to have a result that crosses from one case to the other uniformly. But so here are the notes. The proof is very different. In the usual Bronte-March, you parameterize the progression. A concurrent to A modulo Q, you write it as A plus MQ, and then you work on M. So you use the additive structure. And what we do with Priemvad is that we recognize the coset by using multiplicative character. So we use the multiplicative structure. So the proof is completely different from one to the other. It would be good to have something that goes from one to the other continuously. Okay, and then I was in IMSC 2 years ago, I think, and we were talking about this problem with Priyamvad and Balu, and finally we got the idea that since we are looking at set of densities, we don't need really an individual upper bound for Bronte march, but an upper bound almost everywhere. When I was looking at this paper by Balu and Ramachandra, I said almost everywhere in Y. You can have almost everywhere in Q, I mean A here. Yeah. So what we prove is that we can get the same result. So the factor 2, the phi of Q, like in the usual Bronte march, but x upon square root of Q instead of x by Q. Except that you have this epsilon of A, and the condition here tells you that this epsilon of A is almost everywhere very small, I mean little of 1. It's not new. Huller had started doing this kind of thing in 72. He got this theorem in 72, but he used additive characters while we are going to use multiplicative character. And it has been improved by Iwaniec in 82 and several other papers, by Motohashi and by Mikawa. I'll tell you more about Mikawa later. They use dispersion methods, they use analytic number theory. The proofs that we present, we are able to make it explicit, fully explicit, because we've simplified the proof quite a bit. Yes. Now that's for people who want to see about the engine inside. There's 2 slides where I show you the engine. So what we want to study is the number of primes that are congruent to A mod Q. And instead of having 1 for the primes that are less than x and 0 for the primes that are larger, I smooth this condition because I want to use some Fourier transform, Mellin transform. And they are going to behave better if I have a smoothing function. Okay. And I assume that they are larger than some small parameter z, which is square root of x. This condition is harmless. So the first thing you do in sieve, you use an enveloping sieve, and my favorite one. And instead of having a prime, you relax this condition, you say an integer n, but then you put the sieve weight here. And this weight is essentially telling you that n is going to behave like a prime, but you're going to have twice too many of them. Density has increased. But the lambda d has a very short support. I mean, lambda d is 0 if d is a bit large. That's the good part. So since lambda d is 0 when d is a bit large, you open your square and you put the lambda d in front and put the summation upon n at the back. And you recognize a condition, like I told you. You recognize a condition with characters. Fourier transform is a multiplicative group. For specialists, you have to see that I'm using only primitive characters because of a trick that we introduced with Rumley a long time ago. Anyway, it only simplifies the proof. And then you push your things and you guess that the principal character is going to give the main term. That's this guy here. And then you put everything in E of A, that's an error term. And this error term has an expression like that with L functions. And then you want to compute the L2 square of that. So if you forget summation upon R here, you have summation upon chi, and you have some orthogonality with respect to chi. And then you have an integral with L1 and a short Dirichlet polynomial. That's what you have. So what you do next, of course, is you use Cauchy to use orthogonality of the characters, do a bit of something more, and you reach this expression. Okay. At this time, essentially, everyone doing analytic number theory would have reached this point. If you decide to take the multiplicative path and not the additive path, you reach this point. And then you have to think a bit. You can be impressed by L1 chi and you want to use the fourth power moment for L1 chi. for LSK. And then you get to Moto-Hashis proof. But in fact, there's a simpler way. You can simply take the L infinite norm of LSK out, and then you're left with a square here, Dirichlet polynomial with a square. And for that, you have the hybrid Larchiv inequality of Gallagher in 70. It turned out that I worked out an explicit version of it. So everything is ready to be used. Except that when you do that, you have what? You have L2 norms to compute. So the L2 norm to compute is this one. The big guy is here. And the big guy, lambda d is about 1, let's say, first approximation. So the inner sum is about 3 to the omega n. Square, that's about 9 to the omega n. The sum upon n of 9 to the omega n is going to be z squared times log z to the 8. When you do some computation, you discover that it's about z squared upon log z to the cube. It turns out that, in fact, my co-authors managed to prove that this sum is indeed less than z squared upon log z to the cube, and explicitly. I mean, you have to realize that you have to save 11 powers of log. It's, at the beginning, when Priyamvad told me that he was able to do something, not the full result, but still, I told him that his proof was wrong. But I was wrong. So we're still working on that. There's also a very difficult part, which is to compute it. We would like to compute it for z up to 10 to the 5 or 10 to the 6, and I'm able to go till 10,000 and nothing more. Something else, to achieve this bound, we need to take a simpler version of lambda d. So we take mu of d log z by d when z by d is larger than 1, divided by log z. But then you have the difficulty of computing the main term. But the main term, thanks to some earlier work of mine, that's nice. So several things, several little bits fall together to give this result. You can compute it easily. And then there's some, anyway. So this proof is done. Now I would like to tell you a bit more about accumulation in subgroups. Yes. And for subgroups, I've taken a picture of Mizoram. That's a picture from Rayek in Mizoram. But I'm cheating because I didn't go there by hiking. I got there on a scooter, in fact. It's still beautiful. Okay. So the large subgroup problem. Typically, what we have assumes that takes the classes reached by the prime, say less than q to the 3 halves. And if by bad luck, your set A is included into two cosets, h times uh, where h is a subgroup of index 5. Well, it gives you 2 upon 5 phi of q element, which is still larger than 1/3 phi of q. And if you look at the threefold sum, you discover that it's included in h times times u squared times u cubed, and u4h is missing. So you have to avoid this case. And that's one of that's a large subgroup problem. What happens when A falls into a finite and small union of large index subgroup? So Priyamvad, by adapting some work of Elliott, managed to prove that if you look not at coset but at subgroup, okay, every subgroup contains the primes less than q to the y minus 1 by 3, and y is index of the subgroup. So for y equal to 5, 5 minus 1 is 4, and you have 4/3. Okay. If q is cube free, you have something better with Burgess inequality. The work of Elliott was only for q to being a prime, and needed some tending to force up the proof. And also it was not for a subgroup, it was only for cube, for kth powers. Anyway, but what is really, so if y is 11, for instance, the next case after y equal to 5 is y equal to 8 and then y equal to 11. So for y equal to 8, you get q to the 7/3, which is huge, it's larger than 2. So this result is not so good. That's the best we get, but it's really as soon as y is equal to 8 or 11, it's awful. If you use algebraic number theory, for instance, if you look at indices of index 5, subgroup of index 5, let's say Q is a prime, is a group of fifths power. So you have some algebraic property of it. Of this element are fifths power. There's a nice result of Nagel that I always quote in 52. Take a prime which is congruent to 1 modulo Q. Then you can write 4Q as being a square plus 27b square. And the incredible found of Nagel is that any divisor of AB is a cubic residue. So any prime divisor, by the way, but any prime divisor of AB is cubic residue. So you see, if you use algebraic number theory, you get much better results. Much more, you can even get an example. Get a square, get b square, and then you'll get a prime. Sun has gone into this direction for quartic and residues. And Bentley and Pollack, they published some result for quartic residues, and they're still extending this proof that uses quadratic reciprocity. My guess is a bridge between these two methods, analytic one and algebraic one, would be is a good thing to do. Okay, I'm out of time, so let's see what I do. Okay, we'll just add another ingredient, because what we've been seeing is that we're able to detect whether we have a prime in an arithmetic in a subgroup. Okay, but we have difficulty with cosets. So what can we do with cosets? If you think about the Bronte inequality, I told you that it tells you, in fact, that what you count is primes or product of two primes. And you look at this ID and you discover that using the idea of preemvad and this Bronte stuff, you can prove that if you give yourself a coset which is of a subgroup which is of large index, y is large, then you can say that UH contains a prime or product of two primes, all of them less than Q, both of them less than Q. So it tells you that your residual set not only has a density, but it has some structure. When you multiply it by 2, you cover everyone. When you take a square of this set, you get everyone. And okay, Hisbron has already obtained an exponent less than 2. But when we restrict ourselves to coset, we can find P1 and P2 less than Q and not Q square, which is, of course, what we want. Okay, and then I'll maybe finish on this one. Yes, we can do some additive combinatoric in this new setting. In this new setting, you have your set A star. So that the primes that you reduce modulo your subgroup, and you want the threefold sum in additive notation, A star plus A star plus A star, to be equal to G star. You want to cover everyone with product of 3. So assume you don't cover them. But you know by these P2 numbers that A star union 2 A stars covers everything. So what happens? Well, what happens is that in fact you discover that A star, the condition 3 here, A star is a sum-free set. That's the incredible part that we had overlooked till now. And you discover that in this case, 0 doesn't belong to A star. So it means that if you want to avoid the case 3 A stars not equal to G star, you only have to prove that you have a prime in a subgroup. And you don't have to care about cosets. That's the beauty of it. Okay, let me skip the next part and go till the end. Okay, no worry, no worry, no worry. Here, yes. Because since we have this new way of handling congruence classes, we wanted to see what was happening in a different setting. With Shaoli Gun and Josta Sivaraman, we looked at what happened in the narrow class group HQ. So the gist of the proof goes through, and of course you have specific difficulty to adapt the argument to a number field, and that's what really is interesting. So what we have, if the proof is correct, at least, now we can find primes that are completely split. That's what you want. So that and the norm of each of them is bounded by the norm of q to the power 6. And you know that these primes belong to the specific class of HQ that you've chosen at the beginning. In the number field case, this result is much better than the exponent you get when you take only one prime, which must be something like 40. So this 6 is much smaller, and I think that we are going to get an even smaller exponent soon. But well, we have things to do, and the proof will come. Okay, and that's all. And I have 1 minute over time. Thank you.
Thank you, sir, for a wonderful talk. So, any questions here? So, Vishwanath then have one question.
So I just have a very quick question. You mentioned a bit about parity problem in the beginning.
Can you speak loud, because I hear very
Is this better?
a bit better?
Okay. So I just have a quick question about the parity problem you mentioned in the beginning.
Mm-hmm.
We expect somehow the product of prime numbers, when it's odd and when it's even, the upper bound by C to be off by a factor of 2.
Mm-hmm.
I don't see why that. I mean, can you just quickly explain why that is expected? I mean, the issue.
What happens is that when you do sieve, you start from the integers, you remove the integers that are divisible by 1 prime, yes? Then you discover that you've removed twice the integers that were divisible by 2 primes. So you add them, and then you remove the ones that are divisible by 3 primes, and then you add the ones that are divisible by 4 primes. So you see that the parity comes between the upper and the lower bound. It could be made much more precise. If you look at Selberg's identity, you'll find it in literature. It tells you that if you take the sum of lambda n plus the sum of log of p plus sum of log of p1 log of p2 for p1 p2 less than x, this one is equal to 2x log x. And this can be proved without using the prime number theorem. I would need more time to go further than that, but we have several instances, several hints that tells us that it is like that, but it's not something precise enough.
But we expect that to happen with the best bounds that are available, right? Otherwise, if it's just a rough bound, expecting that to be off by a factor of 2 doesn't sound right. I mean,
sorry, if
do we expect the factor of 2 issue to happen only if we are comparing the best bounds for any set, the product of primes in that set? Because otherwise, if it's a rough bound, then it need not necessarily be differing by.
No. We expect it even in large subsets. I'm sorry, but I don't hear enough. I'm sorry.
Akhilesh, maybe you can repeat the question for him on behalf of him.
So speak loud.
So am I audible now? Not clear?
That's a bit better.
A little more?
Okay, go.
Yes. So I was just saying that if you have any set and you want to compare the number of primes or the number of product primes in that set and you use this method, do we expect the bounds to be off by a factor of 2 for the best bounds or for any? Because it sounds like it should be done for the best one.
Well, it depends how general is your set, because we know the prime number theorem, and in the prime number theorem we don't have the factor 2. Yes. What is the parity principle telling you is that if you use a combinatorial method only, you'll have difficulties overcoming this factor 2, and usually it is because when you look at the machine you build, it is insensitive to the parity. If you don't put something special inside to control the parity, what you get is not going to give you to be able to distinguish the number of prime factors. It's rather surprising. Selberg was surprised at the beginning about that, and it has been investigated. It seems that the elementary machines, the combinatorial machines we are making, we are building, are insensitive to this character.
Okay.
There is one question in the chat box. Sir,
Mhm.
can you hear? There is one question in the
Yes.
chat box. Maybe you can open the question there.
Oh, I doubt. Can you repeat it?
Okay, this is Jean-Marc asked the question. What about replacing the product of 3 primes by a product of at most 3 primes? Replacing product of 3 primes by a product of at most 3 primes.
Yes. Wait a minute. Okay, with at most 3 primes, with at most 3 primes. I mean, with 4 primes we can. That's with 4 primes we can cover everything. Okay. With at most 3 primes. I don't know. I know with 4 we're able to do it. With at most 3, I'm not sure. My guess is that we don't know how to do it, but I'm not sure.
Okay. Any other questions? No questions here in seminar hall. Maybe we can look any question in the YouTube channel. Srijit, any question in the YouTube channel?
No, there are no questions from YouTube channel.
Okay. So thank you, sir, once again.
Thank you for the invitation, and good conference to you, and have some tea for me, and have some sun for me also.
So, okay, bye.